Hello, welcome to Electronics Education. I am Vincent Chang. Thanks for coming. So today I'm going to continue our learning around the slew rate. Slew rate of IC operational amplifier part 3. Full power bandwidth explained. Full power bandwidth explained. In the previous lecture, I taught you about the slew rate, the definition, the measurement, the cause, the insight of slew rate from the perspective of an internally compensated integrated circuit operational amplifier. So based on that foundation, that insight, then let's start with a follower, the voltage follower. So assuming it's a large signal, again, it's the large signal. Now we're not in the territory of large signal. We have been in the territory of large signal for 3 lectures already, all right? So don't get confused. So now this is about the large signal. So large, low frequency signal. That's what the title says. So think about it, if it's low frequency, low, but it's large. So see, the signal amplitude, because I want to emphasize, give it the sign of large. I use how large? The V capital M. So the V capital M represent what? V capital M represents the rated out voltage. That's already the maximum. The maximum swing, the maximum voltage, rated out voltage. So it's a large signal input. The sinusoidal input, but it's the low frequency. Again, it's a large, low frequency signal. What happened when the large signal, low frequency signal sent to a voltage follower? Then it's gonna be, because it's a follower, right? So it change, I change. It change, I change. So it's gonna be in sync like this. I'm dancing like this, right? So this is input, this is output. All right. Okay. So large signal in, and then large signal out. So now let's start to a little bit math. So this is about an output signal. So follow the frequency and follow the magnitude, the amplitude. So sinusoidal signal with an amplitude of V capital M and angular frequency of omega. So V capital N sine omega t. So now, so the subject of the slew rate is about rate of change. It's about rate of change. Let's try to get the dVo dt. It's omega V capital M, sine becomes the cosine. So it depends on the time. Different time you have different. But what you care about, what we care about is maximum or minimum. Why you care about the minimum or median? We care about the maximum. So we are concerned because we came from the slew rate lesson. We know there's a limit. So the maximum of dVo dt cannot surpass, cannot exceed, cannot violate, cannot cross the limit of slew rate, right? So the maximum value of the dVo dt is when cosine equals 1. So we want to ensure at that condition, in that condition, it still doesn't violate the slew rate limitation, because there's a limitation. when large signal is present. The conclusion of the takeaway of the previous lesson tells us the maximum rate of change when the large signal is present is slew rate. That means the frequency f, 2 pi f equals omega, has a limit. And that limit, the slew rate divided by 2 pi v capital M, is the large signal frequency limit. It's your large signal frequency limit. And that, I hammered this keyword many, many times. You have to get this. So that large signal frequency limit is called 4-power bandwidth. So this is the 4-power bandwidth. It's directly related to the slew rate. And definition, slew rate divided by 2 pi v capital M means the rated output voltage. So two things decide the 4-power bandwidth. Number one, slew rate. Number two, rated output voltage. So now you understand my logic, right? The first lecture about rated output voltage. The second lecture about slew rate. Now the third one, 4-power bandwidth. Now I give you a big picture, all right? Low frequency operation. Let's end this lecture with a big picture. What do you mean by low frequency? Compare with the FM. The 4-power bandwidth. So if it's less than FM, that means what? No slew rate violation. Not suffer from the slew rate limitation. So we can sync. So you change, I change, right? We can dance like this, right? But if the frequency like this, you want to do this, because at least there's a limit, right? Because if you want to do, there's a limit in terms of time, with respect time. But if your sign means not SIGN, the sinusoidal signal. If your sign like this, then what? A high frequency. If you try to do this, then sorry, I can only do this. You got it? You got it. Because your learning is in sequence. So you know the secret behind this. And not the secret, but also the insight. Right? So why sinusoidal in, triangular out? At least you know two things. Number one, slew rate limitation. And number two, that slope of the triangular wave is the slew rate. That's the big picture. So here's the takeaway. Number one, 4-power bandwidth. That's the definition. It's decided by two parameters, slew rate and the rated output voltage. And then if it's low frequency, large signal operation, then it's sinusoidal in, sinusoidal out. But if it's the high frequency operation exceed that maximum frequency limit, then it's going to turn the sinusoidal into a triangular waveform. Takeaway number two. What kind of bandwidth this 1 megahertz is referring to? Full power bandwidth, because in the manufacturer's information, right? Only one word, bandwidth. So what kind of bandwidth? What kind of bandwidth? It's this. Remember this? What is A? What is A? What is A? the gain within what region? Linear region, all right? So this bandwidth, of course, is referring to the FT. And F3 decibel and FT, both are small signal bandwidth, all right? It's the small signal bandwidth. And this lecture is about large signal bandwidth. So don't get confused. I know where's the trap. Where you get confused. So I especially want to highlight at the end. So don't get confused between the small signal bandwidth and the large signal bandwidth. This is something that I want you to take in. In the next lecture video, I'm going to teach another characteristic of a practical operational amplifier called offset voltage. See you there. Thanks for watching.